Good morning, good afternoon, and good evening. I'd like to thank the Technical Program Committee for inviting me to this workshop. The title of my talk is Deep Learning for Inverse Design of Optical Devices. My name is Keisuke Kojima from MERL, Mitsubishi Electric Research Labs in Cambridge, Massachusetts, USA. I was also a visiting scientist at UC Santa Barbara in the first half of last year. This is a collaboration work between MERL, UC Santa Barbara, and Purdue University. And I would like to thank everybody for this collaboration. This is the outline of this talk. First, I will talk about the introduction, deep learning and photonics. Next, I will talk about the nanophotonic power splitter. Then, for the regression model, inverse regression model, generative model, conditional variational autoencoder, CVAE, adversarial CVAE plus active learning, and summary. Now, machine learning has been studied for many years for many problems. That includes k-means, Gaussian mixture model, principal component analysis, independent component analysis, support vector machine, self-organizing map, hidden Markov model, and artificial neural networks has been studied for over 40 years. Now, in the past 15 years or so, the so-called deep learning or deep neural networks have been studied for many applications very successfully because of the new development of algorithms and GPU hardware. It is a kind of ANN, but has more layers and is more complex. In the right figure, each layer has different tasks, and the combined deep neural network can perform very advanced tasks. Now, this figure shows the number of publications using Google Scholar as a function of year. The top black line uses a combined word of machine learning and optical communications. The red line uses a combined keywords of deep learning and optical communications. As you can see, deep learning is penetrating into the area of optical communications very rapidly, with an average increase rate of over 300%. Now, the black dashed line shows the combined keyword of machine learning and optical device. The red dashed line shows the combined keyword of deep learning and optical device. It is also growing rapidly and is about 1.4 years behind the optical communication. If we are talking about neural networks and optical devices, there are two categories: neural networks accelerated by optical devices, and acceleration of the optical device design by neural networks. For the first category, I was part of the team of Mitsubishi Electric Lab in Japan when we first demonstrated the world's first integrated optical neural chip back in 1990. However, for the rest of this talk, we will discuss the second topic, that is, acceleration of optical device design by neural networks and specifically deep neural networks. Here I will talk about the nanostructured integrated photonics examples. This is a polarization beam splitter. It was designed by Direct Binary Search, DBS, to optimize 20 by 20 data. This is an example of 1.3, 1.55 micron wavelength splitter. It was designed by the joint method. In most cases, for optimizing the device structure, we need to try a large number of initial conditions to achieve very good results. So it is a time-consuming process. Throughout this talk, we will be using this nanophotonic power splitter structure. The target splitting ratio is arbitrary. For example, 121, 122, and 123. We'll be shooting for low excess loss and low reflection. This can be a key component for the future complex photonic integrated circuits. The fundamental question is, if we give discrete set of training data, can we generate devices of arbitrary splitting ratios? Can we generalize? The device is made of 2.25 micron square area made by 220 nanometer thick SiO with SiO2 cladding. We will use numerical FDTD for 3D FDTD simulations. In this talk, we will show you 3 different neural network models for the inverse design of nanophotonic devices. This is a forward regression model where the input is a device structure and the output is a device performance, which is the transmission and the reflection spectra in our example. The second model we'll be showing is an inverse regression model where the input is a device performance and the output is a device structure. The third model we'll be using is a generative model based on the autoencoder. Once the autoencoder is trained, the target performance and Gaussian noise is given to the decoder to generate a series of very good device candidates. For the deep neural networks, because our device structure is very analogous to two-dimensional images, we will use convolutional neural networks, CNNs. As shown in the bottom of the slide, compared to the fully connected DNNs, CNN shows much smaller prediction error. This shows how a forward regression model can be used in the inverse design. We use a feed-forward DNN, more specifically CNN, in our case. The DNN used with an optimizer, in our case, direct binary search, to get an estimate of each structure performances very quickly. We sometimes use an actual 3D FDD simulations to get more accurate performances. The FDTD results are used in updating the DNN. For the DNN, we use 11,000 training data. By flipping the structure, we double the number of the training data to 22,000. Here we plot the splitting ratio in the horizontal axis and the total transmission in the vertical axis. Our target splitting ratio is 0.27, where the training data does not exist, and the target transmittance is as high as possible. We start with these 3 initial conditions as shown in the red circles. This is the plot of the metric as a function of the number of the 3D FDD runs. Here, the metric is a mean square error of the worst case T1, T2, and the reflection compared to the target. This dotted line shows a metric when the conventional DBS is used. The solid line shows the metric when deep learning assisted DBS is used. Here, we conducted DBS for all 400 holes possibilities using DNN to estimate the metric, and then use FDTD to verify the result. One 3D FDTD takes about 2 minutes on a desktop PC. For the case of a deep learning assisted DBS, the initial training takes about 1 hour. After that, for each DBS step, we have an overhead of about 20 seconds including 400 estimations using DNN, as well as retraining the network. So the overhead is about 20%. As you can see, deep learning assisted DBS achieves quicker and better results. This is an example of the optimized simulated device performance, where the total transmittance is over 87.5% for the wavelength range between 1.3 micron and 1.8 micron. The reflection is less than 0.5%. The second model we'll be talking is an inverse regression model. This is also on CNN. We train the network with the performance as input and the device structure as an output. Once the network is trained, we give target performance as an input and we get semi-optimized device structure as an output. In reality, in most cases, we do not get optimized results. So we give a series of slightly different target performance values as an input and obtain a series of semi-optimized structures. We verify these structures by 3D FTD simulations, and we update the network by including these in the training dataset. It's called active learning. This is the training data used for the inverse regression model. We are using the same training data as the first forward model, and the target is also the same. As inputs, we give 40 different sets of T1 and T2. And then we obtain 40 outputs, that is binary fold vectors. These are verified by 3D FTD simulations. We add those points to the training data and retrain the network. We then run the second round, and the purple points indicate the new output data. Some of these also fill in the gap. The light green points show that the results are even better after the third round. So we verified that the inverse regression model can generate data which did not exist in the training data. In order to verify our concept experimentally, we prototyped the splitter using e-beam lithography. It was fabricated through a multi-project wafer by Applied Nanotools, a company in Canada. The device was designed by the inverse regression model. It was optimized for 1:3 splitting ratio with a 2.6 micron square device. The solid line in the right figure shows the measured transmittance from each port, and the dashed lines show the simulated transmittance. The measurement agrees very well with the simulations, and we verify that our design cost methodology works well. So far, we use DNNs as regression models. For designing materials, structures, devices, use of generative deep learning models are beginning. For example, designing plasmonics and metasurface optics now uses generative models. Conditional variational autoencoder, CVAE, has been used by Northeastern University, and generative adversarial networks, GANs, are being used by Georgia Tech. In this section, we first use CVAE for the power splitter problem. Then we identify some limitations for our purpose and use adversarial censoring to overcome the limitations, and add active learning to further improve the performance. This is a simple visualization of an autoencoder. We have a pair of an encoder and a decoder. And we have fewer number of latent variables than the input and output neurons. We will train the network using the same input and output, for example, 1. And we repeat with other input-output pairs. This is essentially a dimensionality reduction and is analogous to PCA, principal component analysis. The next step is variational autoencoder. Here, after the training, the latent variables can be sampled as random numbers with mean and variance to generate outputs. In order to enable backpropagation, we use the so-called reparameterization trick by approximating z as mu, that is mean, and the Gaussian noise times sigma. Now, we would like to generate output by giving labels. So we use conditional variational autoencoder called CVAE. In this case, we add label next to the latent variables and optionally to the input side during the training phase. After the network training phase, for the data generation phase, we give a label and a Gaussian noise, and in a perfect world, we always obtain very good result matching the labels. In reality, we sometimes obtain wrong result. We will explain more. This is actual network configuration of the conventional CVAE. We have an encoder and a decoder. The optical response, called a label or condition S, is a transmission and a reflection data and has 63 data points and is converted to 9 output through a fully connected layer. And it is added to the input for the decoder. The issue here is that the condition S leaks into the latent variables, compromising the results. This is a network configuration of our proposed adversarial CVAE. In order to reduce the leakage, we add an adversarial block and extract condition S tilde. We also add another channel to the input taken from the condition S. More theoretical background and its first application to brainwave classification are explained in these papers. The loss function for training the conventional CVAE is shown here. The first term is cross entropy loss, enforcing the input and output to be as similar as possible. The second term is KL divergence. This enforces the probability of distribution of the latent variables to be similar to the normal distribution. The figure of merit used here is mean square errors compared to the target spectrum, summed over the whole spectrum. The loss for training the adversarial CVAE has an additional term. This is an MSE loss of S and S tilde. This basically enforces S and S tilde to be as orthogonal as possible. These are the hyperparameters for the adversarial CVAE model. For example, the input shape to the encoder is 2 channels times 20 by 20 data. The number of convolutional layers for the encoder and the decoder is 2. I'm afraid that I do not have enough time to explain all of these, but they're included in our paper to be published in Laser and Photonics reviews soon. Now we show the result. This figure shows the figure of merit plotted against the splitting ratio. The stars show the obtained results from the conventional CVAE model for each splitting ratio. The open circles show the adversarial CVAE model results. This indicates that the adversarial CVAE indeed improves the FOM significantly, especially at the splitting ratio of 0.8. Now we apply the active learning concept. Using the original 15,000 training data, we trained the adversarial CVAE network. Then we generate a total of 1,000 data points through the data generation process. Then we use 3D FTTD for verification. We add these newly obtained 1,000 data points to the training set and repeat this process called active learning. The triangular data points show the result, and compared to the circles, the benefit of active learning is demonstrated clearly. These are the best results for each splitting ratio. The solid lines show the best result achieved by ACVAE, showing very flat spectral response between 1.25 micron and 1.8 micron. The dashed lines show the best training data near the splitting ratio. For example, if you look at the 8:2 splitting ratio, the adversarial CVAE result are shown to be much better than the original training data, shown here. In order to demonstrate the effectiveness of our ACVAE, we now show the latent variable distribution through TSNE, T-distributed stochastic neighbor embedding. This essentially maps high-dimensional latent variables into 2 dimensions for easy visualization. This is a TSNE plot for the latent variables for the conventional CVAE without the adversarial block. Each color shows each splitting ratio, and the triangular for each color shows the centroid of each group, clearly indicating each group is clustering. This shows that there is a leakage of the conditions of the latent variables, leading to clustering for each splitting ratio. The right figure shows the same plot but with the adversarial block. This shows that the triangles, the centroid of each group, almost overlap with each other. This shows there is much less leakage of the conditions to the latent variables, leading to much less clustering. So the benefit of the adversarial block is demonstrated. This is a summary of my talk. We showed 3 examples of using deep learning for the design of nanophotonic devices. The first one is forward regression model, where we used DNN within the optimization loop. The second is inverse regression model, where direct generation of the device structures is possible. But the series of input data are generated with an ad hoc manner. The third one is the generative model. We used adversarial CVAE plus active learning to generate good devices. Here, systematic and efficient generation of a series of very good device structures is possible. The general framework of these approaches will be applicable to a broad range of other design problems, not just for optical devices. Here, we show a list of our references. Especially the most important paper, ACVAE, is shown here. It is to be published in Laser and Photonics reviews soon. In fact, most of the preprints, not just these, but many papers from our colleagues are also available on www.merl.com. So please check it out. And I'd like to thank you very much for listening to my talk. Now, I'm ready to answer to your questions, or you can send me an email to kojima@merl.com.